This segment is about bit shifting. Straightforward with the clock, somewhat more involved with spontaneously flowing elements. I tried making a 2D pipeline bit shifter, and I succeeded actually, but it turned out to be big, slow, and power hungry. I thought I would figure out something very clever, but I didn't. So 2D pipelining the bit shift doesn't make any sense. What ultimately did make sense is what I'm going to show here. And I'm going to show it in three forms. The first is with the free-flowing digits. The second is with the full word completeness of the digits at each shift stage. And the third is the entire shifter as a single combinational circuit. In other words, we only do completeness in the last shift stage. Okay? You know, people tell me I have a hole in my head. I don't think so. The example shift is a left shift end-off 0 fill. It's controlled by a binary shift control, and the shift control is dual rail, so one rail of each bit will say no shift and the other rail will command a shift. And we'll accomplish the shift by selecting one of two inputs to go to each output at each stage of the shift. So this is bit 0, the shift command, and we'll shift by 1. This is bit 1, we'll shift by 2. This is bit 2, we'll shift by 4, and so on. The examples are 32-bit shifts, so there'll be 5 stages here. But we only have room for 3 stages on the page. Now the detail of the select here is over here. So we have the 2 rails of the shift command bit. This says no shift and this says shift. So up here we'll select this, and this will be the straight through. It will be steered to the output. This will be the shift bit shifting into this output, and so we'll select that and it'll be steered to the output. So we get the completeness, and then we close with the bit that we selected, right? So if we selected this one, the closure will go to that, and if we selected this one, the closure will go to that. And you can see up here that each bit is closed individually. The next thing to understand about the way we're doing the shift is that the end-off bits get sunk, right? They disappear. But what we do is we take the completeness of the sunk bits and we run that completeness into the 0 rail of the zero shift in bits, right? So we take the sunk bits and turn them into the 0 bits. And by doing that, we maintain the word width. We don't have, any extra rigmarole because of the sinks and the 0 fills. So we're just doing the word completeness at each stage and doing the acknowledge. Now we're doing the word completeness for the shift command because the 2D pipelining doesn't work. As I mentioned, I tried doing 2D pipelining, but it got too complicated and too expensive. So we're taking full word completeness to close with the shift command bits. Now the program for this is the full word shift. Full word 32f.v, and this is the make command. Now the second example, which is full word shift 32g, we do full word completeness for the input bits, right? We're no longer acknowledging the input bits individually. So we're doing full word completeness for both the input bits and the shift control. So now we have a 3-stage pipeline here. The examples are a 5-stage pipeline. In the third example, full combo L shift 32, the entire shifter is combinational within a single oscillation. We only do a completeness at the end, and we close with the original input flow and all of the control bits all at once. A question of interest here is how will the shifter behave if we drop it into a 2D pipeline flow or a ragged wavefront flow? To look at that, we inserted functions between the test bench and the shifter that created 2D pipelines flow and ragged wavefront flow to present to the shifter. So the 2D pipeline flow, full word shift 2D, contains an incrementer before the shifter, a 2D pipeline incrementer, which increments with 0. So that it doesn't change the numbers going into the shifter so that the test bench still works, but it creates a 2D pipeline flow presented into the shifter. The ragged flow, we inserted a 32-bit adder before the shifter, And the adder had variable carry chains, which presented a ragged wavefront output into the shifter. So we're going to look at the waveforms of the shifters now. And we're going to look at them first in terms of their relative speed executing the test bench. And we're going to look at each one on the uniform time scale, 100 nanoseconds here. So we'll see how they compare to each other. So this is the first shifter with the bits individually closed or acknowledged. This is the second shifter with the bits closed with the full word completeness. Now we were already doing full word completeness for the shift command, so doing full word completeness for the input bits doesn't change that much, right? It's just a little bit slower. This is the third one, which is the full combinational completeness. The whole shifter is in a single oscillation. That oscillation, the period of that oscillation is longer, so it's going to take longer to do the test bench. The next simulation is the shifter presented with 2D pipeline flow. It had the incrementer that was incrementing 0, but generating a 2D pipeline output to present to the shifter. And it doesn't work very well when 2D pipeline flow meets full word completeness flow. And you can see that it takes quite a bit longer here to execute the test bench than the others did. They're up in here somewhere. And the last simulation is the ragged wavefront flow presented to the shifter. And the ragged wavefront flow was generated by an adder with variable carry chains. And you can see that it runs quite a bit faster than the 2D pipeline version, but not quite as fast as the ones that didn't have the ragged wavefront flows or the 2D pipeline flows. Now we'll look in a little more detail at the signals. If we spread out the first simulation, we see that the flow is very regular. If we spread out the second simulation, we can see that it's also very regular, very little change between the two. If we spread out the third simulation, you can see that it's also very regular. These are longer than the others, right? These are shorter, these are longer, right? This is the combinational shifter, and this is the pipeline shifter. Structures to the shifter. And this is the one where we presented the 2D pipeline flow to the shifter. The 2D pipeline flow was presented by an incrementer that incremented 0. It didn't change the numbers, but it presented a 2D pipeline flow to the shifter. So we'll expand this a little bit so you can see the structure of the wavefront flows. So this is the output of the shifter, and this is the input of the shifter. This is the output of the incrementer. And this is what happens when 2D wavefront flow encounters full word completeness. You can see that there's a null between every wavefront flow here. You can see the slanted 2D pipeline flow in the wavefronts, but you can also see the completeness, the waiting for the completeness of all the bits. Okay, so that was presented to the shifter, and this is the output of the shifter. Now you notice the discontinuities down here, and this is where the high order bits came down to present zeros as the low order bits, right? So this was a shift of 1, and this was the 0 shift in from the high order bit to the low order bit. This was a shift of 3, and this is the 0 bit shifted in, and so forth. That's how the shifter works for the input of 2D pipeline flow. Okay, so now we go to the ragged wavefront input, and the input here was from the adder with the variable carry chain delays. And you can see some of the carry chain delays at the output of the shifter. This was the input. This is the output of the adder, and you can see the carry chain delays at the output of the adder. And this is the output of the shifter relating to the carry chain delays. But the output of the shifter is correct. It passes the test bench and it absorbs the carry chain delays. So this is the output of the adder. It receives the ragged wavefronts, absorbs the ragged wavefronts, and outputs a correct result, a wavefront result, even with the ragged wavefronts, right? So the flow completeness relationships just work themselves out. This is a summary of the 5 simulations. This is how long the simulation took and how long the actual test bench took and how long each shift took in each simulation. So 0.69 nanoseconds for the fastest and 1.5 for the slowest, which was the shift presented with the 2D wavefronts. This is the shift presented with the ragged wavefronts, so it's kind of halfway in between. This is the full combinational shift. Okay, this is how much the completeness costs. So this is 5 forward completenesses, one for each pipeline stage in the shifter. And this is 1 forward completeness for the combinational shifter that only had 1 pipeline stage. So the other thing of interest is how many oscillations were in each structure. And the ones that did the closure for individual digits, each individual digit was an oscillation. So this is very fine-grained pipelining. This is the one with this 5 stages of forward pipelining, and this is the one with the whole shift was in a single oscillation.